Just before shooting our video, I want to bring you a couple of teachings or gatherings I've collected today. So the most important one was coming from our colleagues from Enstoi very early morning. Well, he promised that in Czech Republic, beer is cheaper than water. So I'm planning to check it myself later today. And more seriously, I got a comment from the colleague, the executive from Tenet in the panel this morning. He was concerned about the complexity of recycling non-metal materials from cables. I mean, we know that copper and aluminum are easier to recycle, easier to reintroduce into the process with cleanness and pureness. Plastics are less. So hopefully the presentation which follows now will give you some additional ideas about that. So if you can shoot our video, please.
Since 1965, Hanwha Solutions has been shaping the future of materials science, advancing industries, connecting possibilities, and powering progress. From pioneering South Korea's first LDP production to achieving breakthroughs in XLPE and semicon technology, our journey has been one of innovation and excellence. Now, in 2025, we begin a new chapter. Hanwha Solutions Wire and Cable Division is officially established. As an independent division, we are dedicated to the wire and cable business, pushing the boundaries of XLPE and semicon solutions. With top-tier quality, innovation and reliability, we are committed to becoming one of our customers' strongest business partners. With sustainable solutions, from advanced insulation recyclability to low-carbon products, we're helping reshape the cable industry for a greener tomorrow. The future of wire and cable begins today. Hanwha Solutions Wire and Cable Division.
Here we are. So, recycling market. You see from this projection, it is 2020 to 2040, that there is some promising increase of recycling from almost 10% in 2020 to 14% in 2040. And also incineration is expected to decrease a little bit. But without significant policies and industry efforts, most likely landfilling and mismanagement will not decrease over the next 15-20 years. So this is a concerning element which drives our attention into recycling. When it comes to global trends, there are important differences region by region. We all know that the EU is leading many of the sustainable and recycling policies, and proof of that is the ESPR regulation, which asks for at least 25% of recycled products into new designs. We can also mention the packaging and packaging waste regulation, which asks for at least 35% of post-consumer recycled contents. And also in Europe, we have some relevant taxes on non-recyclable products, which are, of course, a great incentive for producers and consumers. In the US, starting from right this year, plastic beverage must include 25% of recycled materials. And when it comes to South Korea, the company is based in South Korea. We have regulations for bottles and packaging since last year. And later, we have introduced regulations for electrical and electronics recyclable, and then lastly, it is expected to be issued some specific laws and legislation similar to the European plastic tax. So everywhere in the world, at different speeds, we are moving towards the same direction. It's worth to mention that the United Nations are thinking at a global recycling policy, which is still under discussion, together with some extended producer responsibilities, which of course are helpful. So different speeds, different scenarios, but one general trend. When we talk about recycling, there are basically two technologies to recycle. One is the mechanical recycling, the other one is chemical. So mechanical recycling, as the word says, it's about shredding a material, washing, and then reprocessing without any chemical processes in the middle. The advantage of mechanical recycling is that it's a continuous process, it's low energy consumption, and it requires an amount of investments which is affordable and limited. The flip side of the coin is that the quality of recycled materials depends highly on the pureness and quality of the raw materials introduced into the process. Chemical recycling is more complex, and still we divide it into two possible technologies. One is starting from a pure polymer, reduce it down to a monomer, and then process it again to a polymer. Well, as compared to mechanical recycling, this is more energy intensive. We could classify like medium intensity. Even more interesting is the other thermochemical process, which starts from any mixed polymers and converts them into basic feedstock, which can be easily fuel or other chemicals. This process is more flexible as far as the input is concerned, but it's high energy intensive. Well, at Hanwha, we have an active collaboration with leading consumer good producers, allowing to recycle plastic materials. The point of attention here is that with repeated recycling, the quality and the properties of these materials tend to degrade. So it's not like an infinite loop process over time. Regarding chemical recycling, we have quite an experience at Hanwha Group. And in this case, we can achieve a higher quality than mechanical recycling, and we can recycle a wider range of plastics. The problem with these technologies is that they are effective on a large scale because they require a lot of capex and a lot of opex in terms of energy consumption. So as you can see, there is no, one best, one worse. It's all about balancing these two technologies in an efficient manner to bring to the market competitive products and a balanced solution. I'm going to talk now about what we do in terms of mechanical recycling, and specifically for the cable industry, how we can produce recycled polyethylene for jacketing applications. We collaborate with leading consumer goods companies to develop sustainable materials using PCR plastics. And we have already developed and commercialized some PCRP products. These are few examples of what we do. Well, in this chart there is nothing about cables. It's about bags, films, packaging, tubes for cosmetics. All this is possible, and it requires different technologies, processes, and output quality. The process itself starts from sourcing the right PCR. I mentioned before that quality of input material is essential for the final result. We select specialized companies which are able to provide and to certify the right guarantee of the input products. And then we tend to combine 50-50 virgin materials with recycled materials to produce new materials for the market. Everything ends up with quality certifications and quality controls to guarantee to the market the maximum pureness. As far as cables, we currently have both high density and medium density polyethylene, which are applicable for different cable designs in the jacket, and all of them target at least 50% recycled product into the material. It's relevant to mention that the target is to have performances and qualities which are absolutely comparable with the virgin material. So not only they meet all the specs, but they are also undistinguishable from the virgin material. Okay, these are the main properties that we target when we mix 50-50 virgin materials with recycled materials. What is worth to mention in this chart is the ESCR, which stands for Environmental Stress Crack Resistant. This is probably the most critical property when it comes to jacket. Well, jacket is meant for protecting the electrical core of cables, so it's very important that the mechanical properties over time do not degrade. And this test is performed over thousands of hours, and it's meant to prevent any cracks or visible damages to the external jacket. The requirement, as you see, the blue line is in the region of 1,000 hours, and we have already promising results over 2,000 hours. So the product is not far from being completely developed and available for the market in the upcoming months. When it comes to certifications, we are under the life cycle assessment certification by third parties, EPD Korea, which is a recognized international entity, very similar to European standards, as well as the Global Recycled Standard certification. These numbers on screen are a first attempt to estimate the net amount of CO2 emission that we can save through this technology. This gap is in the region of 16%, and everything shows that it could be improved over time. So quite a promising result. Well, now I'll start talking about a much more complex chemical and mechanical process. We call it supercritical decrosslinking. When I was at school, they said that once a material is cross-linked, there is no way to go back. Well, luckily, probably 30 years have passed ever since. So now we know that it is possible, and it is possible in an efficient way, which claims sustainability. What is a supercritical fluid? A supercritical fluid is a combination of high diffusion rate fluid with high density. The combination of these properties promises penetrability and reactivity of the fluid, which are essential for recycling. And now I need your attention to go to a graph. I promise it's not rocket science, but please bear with me. We all know that the combination of pressure and temperature can determine whether a substance is liquid, solid, or gas. We also know that there is a magic point called the triple point, spotted there, where there is a unique combination of pressure and temperature, and then at that specific point, liquid, gas, and solid live together. It's like 0.01 Celsius for water, just for your memory. If we move towards the boundary between liquid and gaseous phase, that blue line over there, we reach another point, which is called the critical point. Above the critical point, there is no distinction between liquid and the gaseous phase. And in this area, there are some very special properties displayed by this substance. And these properties are, for example, high diffusion rate and high penetrability, as I mentioned before. And these characteristics are especially effective when it comes to recycling these substances. This is where we play our game. So this process is like in between mechanical and chemical recycling, but much, much closer to mechanical, as I will explain in a few moments. So if you have survived to the graph, I'll move forward and quickly to the conclusions. So what we use, as I said, is a supercritical fluid and its properties to convert cross-linked polyethylene into polyethylene. So as I mentioned before, the target is to start from a cross-link polyethylene coming from the insulation material of a high voltage cable, for example, and to convert it into polyethylene suitable for jacketing applications. We do that through a continuous twin screw process, which guarantees high efficiency and low energy consumption. So this is a picture of a comparative output between a conventional decrosslinking technology and our supercritical fluid decrosslinking. As you can clearly see from the picture, the output that we gather is much, much cleaner, transparent, and very similar to virgin material. So advantages are high efficiency, it's an eco-friendly solution, we have a clear output, and lastly, an effective reduction of the CO2 emissions. Thanks to the efficient heat transfer, and we can also obtain another very important result, which is absolutely not given. When you recycle cross-linked materials, odors, so very strong smell, appear from these recycled materials, and this is a big concern in the shop floor when you reprocess these products. They are pretty much unusable because of their odors. So thanks to this technology, we are able to reduce dramatically these odors to the level of virgin materials and impurities, guaranteeing high quality of the output. This graph, which apparently is even complex than the prior one, but I'll try to make it very easy, shows a comparative of the VOCs. VOCs are volatile organic compounds, so those things that our nose is able to smell. And you can clearly see that the second line from the top is the Hanwha Solutions supercritical decrosslink material, and those peaks represent the amount of volatile organic materials in the air. So clearly that is the winning technology for reducing those odors. Because we want to sell to the cable industry, we have developed two parallel technologies. One is meant for producing a recycled polyethylene suitable for black applications. And this is for, black jackets typical of high voltage and extra high voltage cables, but also internal fillers where color does not matter. But we also know that there is a part of the industry, especially in Europe for medium voltage applications, where the external jacket must be red. And this is a bit more complex process because when shredding, we need to split between semiconductive and insulation materials. It's a bit more energy expensive, a bit more cost expensive, but it's possible. So for all those applications which require starting from a neutral material and then applying master batch, well, yes, there is a solution in case you wonder. This is a comparative data sheet where basically samples number 3 or 4, which are our technology, show a superior output with the main characteristics like melting index and density and hardness, very, very much comparable to pure virgin material. And just to bring my presentation to the conclusion, 2 words about the business model. So we claim a complete circular process from a collection of waste cable into the decrosslinking process, and then the reintroduction to the market with materials which are comparable to virgin materials as far as performance and behavior are concerned. Because proximity is absolutely important in the sustainability process and the recycling industry, we are thinking about possible business model as soon as this technology will be completely developed, which hopefully will happen very soon. These models include technology licensing to any existing waste treatment companies or cable makers, but also could be the occasion to build any recycling platforms closer to the end user regions. And this is pretty much all from my presentation. So thank you very much for your attention, and I will leave you a QR code on screen that you can scan and follow us. Thank you very much.